Probably heard or even pondered this thought that we're just a tiny piece in this huge universe. Now, new research proves
The Hawaii scientists are the first to map a colossal supercluster where our galaxy lies.
This void is expanding at a terrifying pace, threatening to consume our entire galaxy. I've wandered the cosmos for eons, spinning, orbiting, bound by unseen forces I can never escape. I am Earth, and at this very moment, I'm rotating on my axis at over 1,600 kilometers per hour, depending on your location. But that's just the start. I speed around the sun, which blazes a path through the Milky Way. Yet, the Milky Way itself isn't stationary. It's hurtling through the local group, carried by something even more immense. And here's the perplexing part. We're racing toward the Shapley supercluster, an enormous congregation of galaxies. But somehow, the numbers don't quite add up. There isn't enough mass in Shapley to explain why I'm moving this fast. Half of my journey through space is a mystery, pulled by a force I can't see, heading towards something I can't understand. What's out there? And what's dragging me and you through the universe at breakneck speeds? In 2017, researchers identified a potential source for the rest of that motion. But it's not something pulling us. It's something pushing. Join in today as we dive into the evidence for a region of space called the dipole repeller and try to understand how, in a universe dominated by gravity, something could push instead of pull. Let's start with some background. It took astronomers quite some time to recognize this motion. To determine that we were in motion, scientists first had to chart the regions of space surrounding us. Although humans have been mapping the stars for centuries, it wasn't until 1924 that Edwin Hubble confirmed the existence of stars and galaxies beyond the Milky Way. Before his discovery, astronomers observed faint clusters of light in the sky, what we now identify as galaxies. But the prevailing belief was that these were merely gas clouds or spiral nebulae within our own galaxy, rather than distant celestial objects. Hubble observed several Cepheid stars, a type of variable star with a cycle of brightness changes closely tied to their luminosity, inside one of these spiral nebulae. Using this predictable relationship between luminosity and distance, he precisely calculated how far away they were. To everyone's surprise, he proved they had to lie beyond the Milky Way. Since then, astronomers have raced to adapt to this new understanding of galaxies and superclusters, working to map the positions and distances of every galaxy they could detect. Hubble initially focused on Andromeda, our nearest major galactic neighbor, but countless other galaxies existed. By the 1970s, astronomers Stephen Gregory, Laird Thompson, and William Tift discovered that galaxies weren't randomly dispersed throughout space, but instead formed vast superclusters, enormous filamentary or sheet-like structures separated by immense cosmic voids. They were the first to map a supercluster, the Coma supercluster, which stretches across 100 million light-years. Remarkably, 95% of galaxies reside within these structures. It wasn't until 2014 that scientists fully mapped our own supercluster, the Laniakea supercluster, perhaps an unexpected order of discovery. You'd think it would be easier to map regions of space closer to us rather than those far away, right? But surprisingly, that's not the case. Even though other galaxies were discovered nearly a century ago, and the first supercluster was mapped 40 years ago, it took us much longer to focus on our own cosmic neighborhood. Mapping the local universe is far more difficult than it appears, primarily because the Milky Way obstructs our view. Our galaxy is filled with gas and dust, creating regions that are extremely challenging to see through. This issue is particularly severe when observing the Milky Way center, where the blockage is so dense that scientists refer to it as the zone of avoidance. Very little light can penetrate this region, making visibility a significant challenge, one that plays a key role in our discussion, but more on that later. Strangely, studying distant galaxies is actually easier. Astronomers simply aim a telescope at a specific area in the night sky and gather light from far-off objects. However, Mapping our cosmic neighborhood requires scanning every section of the sky, an immense and complex task. Despite these challenges, astronomers are making significant progress. By observing thousands of galaxies in our local galactic neighborhood and analyzing their peculiar motion, their movement relative to the cosmic background radiation, unaffected by the universe's expansion, scientists have been able to group gravitationally bound galaxies into massive structures called superclusters. At the heart of our own supercluster, the Laniakea supercluster, lies a mysterious region known as the Great Attractor. Our entire Milky Way galaxy is gradually drifting toward a region located approximately 150 to 250 million light-years away. However, there's a challenge. The Great Attractor is concealed within the zone of avoidance, making it incredibly difficult to study in detail. But that's not the whole story. The Laniakea supercluster itself is also in motion, drawn toward an even larger cosmic structure, the Shapley supercluster. At its center lies the Shapley Attractor, an area thought to be immensely dense. And just like the Great Attractor, it too is hidden within the zone of avoidance, leaving us uncertain about the exact force pulling us in. While we continue to uncover more about our cosmic surroundings, the Milky Way still keeps some of its greatest mysteries shrouded in darkness. Fortunately, advancements in X-ray and infrared telescopes have allowed scientists to get a clearer view of these two mysterious attractors. But that's where things get interesting. The mass observed in these regions isn't quite enough to explain the motion of our galaxy in that direction. To tackle this puzzle, a team of researchers from the University of Hawaii, Yehuda Hoffman, Daniel Pomereed, R. Brent Tully, and Helene M. Courtois, published a paper in Nature, aiming to shed light on this discrepancy. Instead of just charting the positions of galaxies, the team took a new approach. They mapped the motions of galaxies. By analyzing how galaxies move, they created a flow map of the local universe. After running the data through mathematical models, they could infer the locations of massive structures in nearby superclusters. And what they found was surprising. As anticipated, a significant portion of the local mass is drawn toward the Shapley supercluster. However, an unexpected discovery revealed a substantial amount of mass moving away from a particular region in space. This enigmatic area was named the dipole repeller. Interestingly, both the Shapley Attractor and the dipole repeller contribute equally, each accounting for about 50%, to our galaxy's motion, creating a cosmic tug-of-war, which is why it's referred to as a dipole. But how can this be? Gravity, as we understand it, only attracts. What, then, could be causing this apparent repelling effect? Could it be something exotic, such as a cluster of white holes, the hypothetical opposites of black holes, or some unknown form of anti-gravity? Surprisingly, the explanation is much simpler: emptiness. The dipole repeller is a vast void, an immense bubble spanning approximately 100 million light-years, with few, if any, major galaxies. It is one of the expansive empty spaces nestled between the cosmic filaments that form the large-scale structure of the universe. What's fascinating is that our galaxy's current motion aligns more closely with the push from this void than with the pull from the Shapley Attractor, giving strong support to this theory. So how can nothing push? The answer lies in understanding that this is more of a pseudo-force than a real one. Imagine a universe where galaxies are evenly distributed. In such a scenario, gravity from galaxies above, below, to the left, and to the right would all pull equally, balancing out any movement. But in the case of a large void like the dipole repeller, there's less mass in one direction. This imbalance means that gravity from the denser regions pulls more strongly from the opposite side, creating the illusion that we're being pushed away from the void. In essence, it's not that the void is pushing us. It's that the gravitational pull from everything else is stronger, drawing us away from the emptiness. In a perfectly balanced universe, the gravitational forces from all directions would cancel each other out, leaving you stationary, stuck in perfect equilibrium. What happens if you remove galaxies from one side of this cosmic balance? What if a vast void takes their place? the scales suddenly tip. Without gravitational pull from one direction, the remaining force from the opposite side dominates, unopposed. This imbalance causes matter to shift away from the void, creating the illusion that the void itself is pushing objects outward.